Good morning. Welcome to this series of lectures on differential equations. I am Professor Gopal Krishna Srinivasan from the Mathematics Department of IIT Bombay. So, we shall begin with this series of lectures with a short historical sketch. We shall delineate some of the important things that have happened at the beginning of this era of differential equations and calculus. Then I'll give you the names of a few important mathematicians who have contributed to the study of differential equations. So let's begin. Equipped with his calculus, Isaac Newton, with his laws of dynamics, was able to explain the motion of the planets, the precession of the equinoxes, and the formation of tides. Astronomy, which has hitherto been an empirical science, has turned into a dynamical science. This is a monumental achievement of Newton, which is why he is considered to be very great, not just for the invention of calculus, but for the transformation of thought, the transformation of astronomy as a dynamical science. In essence, what Newton did was, he basically dealt with a system of differential equations for the two-body problem, and he was able to derive the Kepler's laws of planetary motion. So, the origins of the theory of differential equations can be traced back at least to Newton. Now, let me get you to the next slide, indicating some of the names of the masters, the early masters who contributed to this subject. First, you see the name of Isaac Barrow, who was a teacher of Isaac Newton. Some of the ideas of calculus already go back to Isaac Barrow. Then, of course, comes Newton. In 1687, he integrated a linear differential equation. In 1693, you see the name of Leibniz, and he discovered that y equal to tx substitution for homogeneous equations. Then comes a very famous name of Bernoulli. We will encounter the Bernoulli equation later, maybe in the 5th or the 6th lecture, and Bernoulli has contributed phenomenally to the theory of differential equations. Then you see the name of Riccati with his famous equation y prime equal to axy squared plus bxy plus cx. This differential equation is notorious because it cannot be solved. Innocent though it looks, it cannot be solved except in special cases. Leonhard Euler, the great genius, he showed how the Riccati equation can be reduced to a linear equation if a certain solution is known. The list is very long and we must truncate this list because the subject of differential equations is at least 350 years old, and we need to get to the nitty-gritty of this present course, and we cannot dwell any longer on this historical development. I'd like to just give you one reference for the historical developments, the opening chapter of this book by Rabe on differential equations, an introduction to basic concepts, results and applications, the 2nd edition. It has a beautiful historical introduction. Laws of physics, when expressed in mathematical terms, give rise to differential equations. For example, the law of mass action in chemistry gives you the differential equations of chemical kinetics and enzyme kinetics. Models arising in biology, ecology, demography, they all give rise to differential equations. We shall see some of these examples coming from ecological models in the later part of today's lecture. One sees some striking similarities between the differential equations that arise in chemical kinetics and mathematical ecology. There are strong similarities between the two kinds of systems. Mathematical biology has today grown into a vast area, and active research is going on in mathematical biology. For example, E.C. Zeeman succeeded in modeling of the heartbeat as a system of differential equations. Hodgkin and Huxley, for their work of neural impulses, received the Nobel Prize. Then there are problems which arise in geometry. So here is a situation where we see application of one part of mathematics to another part of mathematics. So differential equations are all over the place in the physical sciences, in engineering, in biological sciences, in chemistry, ecology, demography, spread of diseases, growth of tumors, and a whole lot of other things, and yes, problems in geometry give rise to differential equations. So there is plenty of reasons why one must study differential equations. There are persuasive reasons why one must study differential equations. And what you will see in this course is just the beginning, a modest beginning of a very vast area of mathematics. Okay, so let's begin by looking at a very simple physical situation, the simple pendulum. So what does a simple pendulum consists of? It consists of a bob of mass m suspended from a point, as you see in this picture, a bob of mass m suspended by a weightless rod of length L, which is set into oscillations, and this angle, this is the mean position of the bob, and this bob is displaced by an angle y, and it is set in oscillations. You see that the mass of the bob is m, and mg is the weight acting vertically downwards, and mg sine y is the component of this direction, the tangential direction. Now, we would like to show how the Newton's second law of motion gives rise to the system of differential equations governing the motion of this bob or the pendulum. So let's see, the angular displacement at time t is y of t. Okay, and now we observe that the angular acceleration, so if the angular displacement is y, then what is the angular velocity? It is dy by dt. What is the angular acceleration? It is d2y by dt squared. And you have got a force which is acting vertically downwards, and that force is going to give rise to a torque. So what is the magnitude of this torque? The magnitude of this torque is mgl sine y. You have to multiply this by L to get the torque. And now what is the moment of inertia of this bob? The moment of inertia of this bob is ml squared. So let's go back to the slides, and you see the moment of inertia is ml squared. You multiply the angular acceleration d2y by dt squared by the moment of inertia ml squared, and that will be balanced by the external torque, and the external torque is minus mgl sine y. The m cancels out, and you get equation 1.1, d2y by dt squared plus g over L sine y equal to 0. So equation 1.1 is the differential equation governing the motion of a simple pendulum. So this simple pendulum, so the motion of the bob or the simple pendulum is governed by this differential equation d2y by dt squared plus g over L sine y equal to 0. That is the differential equation for the motion of a simple pendulum. Simple pendulum is of mass m, of length L, and set into motion. Okay, so let's get back to this differential equation 1.1. So you see that there are two time derivatives. It is d2y by dt squared. So this is a second order differential equation. All right, and so let's go to the next one. So let us look at one more example from physics. SHM stands for simple harmonic motion. So what is a simple harmonic motion? A particle said to exhibit simple harmonic motion if it moves along a straight line. First of all, it moves along a straight line, and the force acting on the particle is proportional to the displacement from the origin, and the force acts in a direction opposite to the displacement. So the displacement of the particle is y of t. Then the acceleration is d2y by dt squared, and multiply this acceleration by m, you get the force, and this force is proportional to y, and so this force has magnitude ky, and it is going to pick up a negative sign because the direction is opposite. So the balance law gives you m d2y by dt squared plus ky equal to 0. Divide by m and call k by m as omega squared, and we get the differential equation 1.2, d2y by dt squared plus omega squared y equal to 0. So equation 1.2 is the second order differential equation. Why is it a second order differential equation? Because you see that the second derivative appears d2y by dt squared. Alright, so now here we see a second example from physics where we got the differential equation by balance law, by looking at a balance law. So I again repeat that laws of physics, when expressed in mathematical terms, give rise to differential equations, and we have already seen two such examples. Two examples, both of them are second order differential equations. Well, let's move on a little further and again look at examples from physics. But before that, let us look at this simple harmonic motion in a little bit of detail. So the equation of simple harmonic motion is again displayed in the slide. d2y by dt squared plus omega squared y equal to 0. Anybody can substitute cosine of omega t into the equation 1.2 and directly verify that cosine of omega t satisfies equation 1.2. So we call cosine of omega t as a solution of equation 1.2. Similarly, one could try y equal to sine omega t, substitute it into the differential equation 1.2, and one can verify that sine omega t is also a solution of equation 1.2. So we got two solutions, cosine omega t and sine omega t of 1.2. Now in physics, you are familiar with the idea of superposition. So you take superposition of two waves, right? So what is the mathematical meaning of superposition? What does it mean to say that we take a superposition of a cosine and a sine? It means you look at a third type of solution, 1.3, namely a cos omega t plus b sine omega t. So let us take equation 1.3 and substitute into equation 1.2, and you will be able to verify quickly that 1.3 also satisfies the differential equation 1.2. So what have we done? We have now enlisted many solutions of 1.2, namely cosine omega t, sine omega t, and generally a cosine omega t plus b sine omega t, that is 1.3. Notice that in 1.3, if you take a equal to 1 and b equal to 0, we get cosine of omega t. If we take A equal to 0 and B equal to 1, we get sine omega t. And I could give A various values 1, 2, 3, minus half, 1/3, whatever. And you could give B various values 1 upon root 2, 1, minus 1, 0, etc. So for every choice of constants A and B, equation 1.3 displays a solution of the harmonic oscillator equation 1.2. So we have enlisted many solutions of 1.2. In fact, we have enlisted an infinite family of solutions of 1.2. However, let us ask ourselves this question: have we enlisted all the solutions? How do I know that this 1.3 exhausts all the solution? Maybe somebody can be exceedingly clever and produce a solution of 1.2 which is not of the form A cosine omega t plus B sine omega t. This question must be answered. That is, how do we know that if Zt is any solution of 1.2, then Zt is of the form A cosine omega t plus B sine omega t for certain constants A and B? We see that we are naturally led to the problem of describing the class of all solutions. It is not difficult to show that 1.3 exhausts all the solutions of 1.2. Every solution of 1.2 is of the form A cosine omega t plus B sine omega t. This is not difficult to prove, but we shall not do that at the moment. We shall come back to this much later if time permits. We shall instead move on to some more examples. Let us look at some examples of electrical circuits. What is the analog of 1.2? 1.2 is a mechanical system of a simple harmonic motion of a particle moving along a straight line by a force which is linear and in opposite direction. Analog of 1.2 also arises in the theory of electrical circuits, namely the LC circuits. The L stands for inductance and C stands for capacitance. So for a discussion of these LC circuits, I shall refer you to the famous book of Robert Resnick and David Halliday, which I am sure you are all reading currently for your preparations, and the second volume or the third edition. Please pay attention to the edition because this book has undergone several editions. So if you pick up the wrong edition, we will not be able to, we are not on the same page. So I am talking about page 845, equation 38.5 in the third edition of Resnick and Halliday's famous book of physics, volume 2. There you will see a very detailed description of this electrical LC circuits. In fact, he talks about the LCR circuits on page 848. And what are the equation governing the LCR circuit? It is d2q by dt squared plus r over L dq by dt plus q over LC equals 0. Here the R is a resistance, L is the inductance and C is the capacitance. In particular, if the resistance is 0, what happens to the differential equation? You see, the R term, the middle term is not there. The middle term is just not there if R is 0. So what do you have? You got d2q by dt squared plus constant times q is 0. What is the constant? 1 upon LC. 1 upon LC is a positive constant. So you can call it omega squared. So you see d2q by dt squared plus omega squared q equal to 0. But isn't that the same as 1.2? 1.2 reads d2y by dt squared plus omega squared y equal to 0. So you see that the LC circuits that you encounter in electrical circuit theory is the electrical analog of the mechanical system of a simple harmonic motion. So the differential equation is very similar. On the other hand, if you throw in a resistance term, then you have a middle term. What is the middle term? R by L dq by dt is the middle term. So this equation would be a oscillator with a damping term thrown in. So I'll refer you to equation 15.37 of Resnick and Halliday. Now let us leave the realm of physics and slowly move to the realm of biology, specifically mathematical ecology. Way back in 1798, Malthus proposed a model for the population growth of an ecology in which there is only one species of organism. For example, you can think of bacteria, the growth of bacterial cultures. Now, there is only one species in this ecology. This model was also proposed independently by Leonhard Euler somewhat earlier. What does the model say? It says that if y of t is a population of the species at time t, then the rate of change of population dy by dt is proportional to the population present at the time. In other words, dy by dt is k times y for some constant k of proportionality. This is equation 1.4, is the equation of a single species ecology or the Malthusian model. Note that 1.4 immediately gives you that y of t must be a e to the power kt. The equation 1.4 is satisfied by a e to the power kt, a times exponential of kt. So this shows that the population yt must grow exponentially fast. So according to the Malthusian model, for a single species ecology, the population yt explodes. It grows very, very fast. It is e to the power kt. Let us ask ourselves a couple of questions. Is this practical? Can population really grow exponentially fast over an unlimited amount of time? Would nature allow such an exponential growth of population? Would there not be some inhibiting factors caused by, say, limitations of natural resources which will prevent this exponential growth? We know that this cannot continue. The population cannot keep on growing exponentially fast. At some point of time, there must be some mechanism by which this is stopped. Such a mechanism was proposed by Verhulst in 1836. What Verhulst says is that, look at the differential equation 1.4. There is just the dy by dt equal to ky. What Verhulst says is that the right hand side must be modified. You see, when there is paucity of natural resources, when there is paucity of food, then that causes social friction. And that social friction is going to have a negative effect on the growth of population. Therefore, the ky term must be changed to a ky minus ky squared by r term. Look at equation 1.5. The differential equation has changed. The rate of change of population is not dy by dt equal to ky. It is dy by dt equal to ky minus some term. What is the term? Ky squared by r, where r is another constant. This r, the second constant r, is called the environment's carrying capacity. This constant r will depend upon the limitations of the environment in which the ecology is evolving. There is a very beautiful book on mathematical biology by J.D. Murray. I have given you the reference for that. It's one of the most comprehensive treatises written on mathematical biology. and you will find in this book lots of historical details, the various models that various scientists have proposed, the merits and demerits of these various models, the kinds of differential equations that you get by making various assumptions, and so on. Now let us go to another system. Let us go to an ecological system, but this time this ecology contains two types of species, a predator and a prey. For example, you can think of the predator as sharks and the prey as sardines, for instance, or any predator and any prey. You can think of cats and mouse if you like. So let us consider two species ecology consisting of a predator with population xt and a prey with population yt. So for the predators, the source of food is the availability of the prey, and the prey, they are herbivorous animals. They for example, if you are looking at aquatic system, then you assume that the prey lives on algae, for example, natural vegetarian food. So suppose for example there is no prey, suppose Y is not there, then the predators don't have food to eat. So their population will die down exponentially fast. Look at equation 1.6. dx by dt equal to minus ax. That means that the function xt is going to be like e to the power minus at. It is going to decay as time goes off to infinity. In other words, if there are no prey, if yt is not there, then the rate of population of xt will keep declining very fast. On the other hand, if there are no predators, that is if xt is not there, then there is nothing to stop the growth of population of the prey. The prey are herbivorous animals and their population keeps on increasing exponentially fast. For example, you can think of an environment with rabbits and foxes. For example, the prey could be rabbits and the predators could be foxes. The rabbits are herbivorous animals and the foxes are carnivorous. Now let us put these two species of animals together. So the rate of decrease, so 1.6 is no longer true because the predators now have food to eat. So the decline in population, that is the term minus ax, is going to be checked by the addition of a plus bxy term. You see the last line in the slide? The right hand side of equation 1.6 is modified by replacing minus ax by minus ax plus bxy. Mind you, all the constants a, b, c and k are all positive. Okay. Now, what will happen to the rate of increase indicated in the right hand side of 1.7. Now, you have put the predators and prey together. Now, the predators are there, they are going to eat the prey. So, the population of prey cannot keep on increasing like 1.7. The rate of population increase dy by dt equal to ky, the ky term is going to be modified. How is it going to be modified? You are going to be looking at ky minus cxy. You are going to be looking at ky minus cxy. And so the modified system of equations will be dx by dt equals minus ax plus bxy, dy by dt equal to ky minus cxy. You get a pair of differential equations 1.8. Constants a, b, c and k are all positive. Now at this juncture you might ask, why did I put a plus bxy and a minus cxy? Why this quadratic term xy? Why not x squared y? Why not xy squared? Well, these are models and they are not accurate models, first of all. Secondly, let us do a thought experiment. Suppose you have an environment with say cats and mice all over the place. Now suppose the population of cats doubles and the population of mice also doubles, then the probability of a cat encountering a mice is going to go up by 4 times. And then that explains why the XY term. And this interaction between a cat and a mouse is going to be detrimental to the mouse, whereas it's going to be favorable to the cats. So that's why in the first equation you see this term with a plus sign, and the second equation you see this term with a minus sign. So that sort of empirically explains this model 1.8. This model is a very famous model. It is called the Volterra-Lotka model. It's a Volterra-Lotka system of equations. It's a system of simultaneous differential equations, and it's a coupled system of differential equations. Remember, look at the first equation in 1.8. It is dx by dt equals minus ax plus bxy. The y appears in the first equation also. And the second equation is dy by dt equal to ky minus cxy. The x appears in the second equation. So the system of equations are a coupled system of equation, namely both unknowns x and y appear in both equations. And this is a simultaneous system of differential equations. And this example I have given just to illustrate how differential equations arise in the study of ecological systems. We are not going to analyze this equation 1.8 in detail, because that's not quite in the scope of this course, but this example has just been put here to show that differential equations are all over the place. Again, they appear in physics, as in electrical circuits, mechanical systems, they appear in the growth of bacteria and population models, demography, spread of diseases, chemical kinetics, and a lot more and a lot more. Alright, so I would like to close this brief discussion of biological systems, how differential equations arise in biology. I spoke for quite some time on this, so it only makes sense to give you some references which you can read at some point of time. There are hundreds and hundreds of books written on mathematical biology, and I have selected 3 of them. The last one is a very nice book by J.D. Murray, which I already mentioned, and the first book, D.S. Jones, M.J. Planck and B.D. Sleeman, says Differential Equations and Mathematical Biology. This book gives you large number of systems of differential equations arising in various biological problems, such as the growth of tumor, for instance, spread of diseases, and many other biological systems have been discussed. Biological differential equations arise in physiology, blood flow in the aorta, that gives rise to interesting systems of differential equations. And a whole book, a very fat volume, has been written on mathematical physiology by Kiener and Schneid. Of course, we are not going to say much more about these things. So this is an introductory lecture on how differential equations arise, the genesis of differential equations, the origins of differential equations. So now let us come to specific differential equations that are relevant for this course. So now on, we are going to study only differential equations of the first order. How does a differential equation of first order look like? dy by dx equals f of x comma y, equation 1.9 that you see on the slide. This is a first order differential equation. This is the first order differential equation because only one derivative appears, dy by dx. In contrast, the SHM, the simple harmonic motion, the equations governing the simple harmonic motions, the equation governing the motion of a pendulum, the LCR circuits, inductance, capacitance, resistance. All these systems involve differential equations with 2 derivatives. So they are second order differential equations. Before we take up the study of second order differential equations, it is natural to begin with first order differential equations, the easier ones. And in this course, that is all that we will be looking at. For second order differential equations, you need to look beyond the present series of lectures. So f of xy is a function of two variables. So we shall primarily be looking at three types of differential equations 1.9, namely those differential equations which are called the variable separable equations. And the second type of differential equations is known as the homogeneous differential equations, and the third is the linear equations and their close cousins, namely the Bernoulli equation. Remember that right to the beginning I put down the name of Jean Bernoulli, who was a very important figure in this historical development of differential equations. It is the same Bernoulli, so his name appears now. So linear equations and Bernoulli equations. So we shall look at these three types of equations in this course. Okay, so let us take up the first one, the variable separable equation. Alright, so the variable separable equation. So this is a very special type of differential equation where the right hand side f of xy, the right hand side f of xy could be a variety of different functions, right? F of xy could be x squared plus y squared, or f of xy could be x into y. F of xy could be sin x into cos y, for instance. So these last two cases are very special. What is special about it? The f of xy is a function of x times a function of y. But in the first example that I gave you, f of xy equal to x squared plus y squared. This is not a product of a function of x and a function of y, correct? So, but what is the variable separable equation? The equation 1.9 is a variable separable equation if f of xy is of the form as of hx into gy. That is, sorry, gx into hy. So, the case when the function f of xy appearing in 1.9 is a product of the form gx into hy, then we say that the differential equation is variable separable, right? Okay. So, in 1.9 f of xy is gx into hy, right? It is going to be gx into hy. Let us write that down. So, you are looking at dy by dx equal to f of xy, and I am assuming that this f of xy is of the form gx into hy. So, what am I supposed to do next? I will divide by h of y, and I will write it as 1 upon h of y into dy by dx equal to g of x. Of course, I am going to assume that h of y is not 0. I am going to make that assumption. What's next? That's a function of x and y. The solution is also a function of x, and h is a function of y, and y in turn is a function of x. And I'm going to integrate both sides with respect to x. So you see, equation 1.10 I divided by h. I'm going to assume hy is not 0. In fact, we're going to assume that neither gx is 0 nor hy is 0. What happens when one of them is 0? That we shall take up later, and such cases will always arise in any mathematical analysis. When you divide, you will have to look at those special cases where the quantity by which you divide is 0. Those cases are always dealt with separately. We shall do that later. So, let us not interrupt the flow of argument. So, we divide by h of y and you integrate both sides of equation 1.10 with respect to x. What do you get? You get 1 upon hy dy by dx into dx equals integral gx dx. Now, look at the left hand side. The integral on the left hand side is very special. It is very tempting to apply the substitution theorem. It is very tempting to apply the substitution theorem. So that y of x, remember h of y and y is a function of x. Y is a function of x, you want to put y of x equal to u. If y of x equal to u, then dy by dx will be du, right. So our integral on the will transform to dy by hy equals integral gx dx. So that's a substitution theorem. But before you apply the substitution theorem, you should be careful that the derivative should not be 0. The change of, what is the substitution theorem? You are making a change of variables, right. For example, recall in your integral calculus, you want to integrate square root of 1 minus x squared dx. You will say put x equal to sine theta. Well, you can put x equal to sine theta as long as you are working in the interval minus pi by 2, pi by 2. The change of variables x equal to sine theta, the derivative must be non-zero. In other words, dy by dx must be non-zero. Go back to the differential equation 1.10. We are already assuming hy is not 0. Now we are going to assume gx is not 0. So your dy by dx is going to be non-zero. The substitution theorem is valid. And so we get equation 1.11. Okay, now what remains? We need to integrate gx dx on the right hand side, and we need to integrate dy by hy on the left hand side. Hopefully we can perform these integrations and hopefully we can get a closed answer. But you know from your experience that these are only hopes and they cannot always be realized. You know of many examples of functions whose indefinite integral gx dx cannot be computed, or its computation can be pretty tricky. Sometimes they are easy, we are lucky if they are easy to compute, these integrals are easy to compute. Often we are not so lucky, either it requires some very clever manipulations and sometimes it is just not possible to compute the indefinite integral. But that is life, we have to accept it. Let us look at a simple example, and usually what happens is a differential equation comes equipped with some initial conditions. Well, I'll come to the solved example after this comment. We think of the variable, the independent variable as time, right? And the dependent variable is, say, the population at time t, as we have seen, or it could be the current flowing through an electrical circuit, or it could be the displacement from the mean position of a simple pendulum. So what we need to do is that we need to think of the independent variable as a time variable, and at some point of time, say time t equal to t naught, you need to be given the data such as the population at time t equal to t naught, the angular displacement at time t equal to t naught, or the concentrations of chemical reactants in a if you are studying chemical reaction, then the concentration of the various substances, reacting substances, they need to be specified at a certain time t naught. Or the current, if the study is of an electrical circuit, then the current at time t equal to t naught may be specified. So you need data at time t equal to t naught, that is the solution that you are trying to find should be prescribed at least one particular point of time, say time t equal to t naught. In other words, you are given the value of y at time t equal to t naught. You are given the value of the solution yt. The solution yt is prescribed at time t equal to t naught. And what you do is you look for the solution in an interval t naught minus a to t naught plus a. So normally differential equations come equipped with certain side conditions such as initial conditions. In other words, you're not only looking at the differential equation, you're not only looking at the differential equation dy by dx equal to f of xy. This is supplemented with some extra condition like y of x naught, where the value of the solution y at x equal to x naught is given to you, say y naught. There's one piece of warning that you see, even if the differential equation is defined everywhere, the interval I on which the solution makes sense may be limited. Let us see this in a very simple and special case. Let us look at the differential equation dy by dt equal to y squared. It's a very innocent looking differential equation. Dy by dt equals y squared. And let us say that the value of the solution at time t equal to 0 is c, where c is a constant, and assume that c is a positive constant just to fix ideas. Then proceeding as above, what do you mean proceeding as above? We divide by y squared and integrate both sides with respect to t, right? We divide by y squared and integrate both sides with respect to t. So let's do that. So we're looking at dy by dt equal to y squared, y of 0 equal to c. So we divide by y squared, 1 upon y squared dy by dt equal to 1. So integrate with respect to time t, both sides. Get integral 1 upon y squared dy by dt equals integral dt, right? That's exactly what we did. Now this one, the left hand side will simplify to integral dy by y squared, thanks to the change of variables substitution theorem. I'll give you this. That's exactly what you see in the slide. You see dy by y squared equals dt. Integrate, and remember the constant of integration. These are indefinite integrals. So there will be that constant of integration floating around. So let's do that. Let's put in the constant of integration and see what happens. So you're looking at integral dy by y squared equal to integral dt. So what happens? Minus 1 upon y equals t plus b, where b is the constant of integration, correct? So that reads y of t equal to minus 1 upon t plus b, right? Now put in the initial conditions. Remember that we are given initial conditions. Put t equal to 0. What do we know when t equal to 0? We know that y of at t equal to 0 is c. So what do we get? C equal to minus 1 upon b, or b equal to minus 1 upon c. The value of the arbitrary constant has now been computed. We have calculated the value of the arbitrary constant, integration constant. Alright, now let us feed back into this. Put this value back here. What do we get? We get y of t equal to minus 1 upon t minus 1 upon c, or it will be c by 1 minus ct. So that's a solution of the differential equation. That is the solution of the differential equation. That's a function. Notice that what happens if t approaches 1 upon c. What happens when t approaches 1 upon c? What happens to this object here? This thing blows up to infinity. That thing blows up to infinity. So here you see this in the slide, I had commented this in red as t tends to 1 by c from the left. That is, t starts at the origin and it progresses and time evolves, and when time t approaches 1 by c, what happens to the solution? The solution simply goes off to infinity. The solution escapes to infinity in finite amount of time. So the solution, the physical system makes sense, the evolution of the physical system makes sense only up to time t equal to 1 by c. Beyond t equal to 1 by c, the physical system has already exploded. There has been a catastrophe. Okay. So the time, the interval on which the solution exists is not the whole real line, it is all the way from minus infinity up to 1 by c, not beyond. This is what the caption says, the solution escapes to infinity in finite time. Solution escapes to infinity in finite time. So let me just go back to the previous slide and now let us look at the warning. Even if the differential equation is defined everywhere, look at the differential equation. The differential equation is dy by dt equal to y squared. There is nothing wrong with the differential equation. Y squared is defined everywhere. The differential equation is defined everywhere. Nevertheless, the solution escapes to infinity in finite time. So even the differential equation is defined everywhere, the interval I on which the solution makes sense may be limited, and that is exactly what happens in this very special case. So we'll stop this first lecture here and we'll continue this in the second lecture. Thank you very much.